We now progress to our final chapter in this unit, which are the benchmark simulations. We have used two different software tools for our benchmark simulations, both of which are open source and freely available. The first one is Lights. We have shown tutorials on how to use this tool already in our first DEM MOOC on the fundamentals. Here we have just added a link to the public GitHub repository from which you can download this tool. The second tool is LMGC90, which implements the non-smooth DEM that we have introduced in the previous part of the present unit. This slide summarizes relevant details of the LMGC90 code. One can access the code and some other resources from this GitLab website of the University of Montpellier in France. For the visualization of LMGC90 results, we have included some hints in the resources LMGC90 MD file, available to you via the iMooX page. Resources related to the analysis of the LMGC90 results are also available. See the Python tools file available in the iMooX page of this unit. Let us now dive into the first setup that we have identified as a useful benchmark. This is a uniaxial compaction process. The simulation parameters of this setup are as follows. The geometry consists of the box with a length of 10 units that is centered in the XY plane and it extends into the Z direction. Periodic boundary conditions similar to the discussed Lees-Edwards boundary conditions, but of course without shear, are imposed in the X and Y direction. The top wall moves here in the Z direction, as it's illustrated here, and in the main combustion cycle has a velocity of minus 0.1 meters per second. During compaction there is no gravity. However, we will use gravity for insertion purposes to quicker dissipate energy, as you will later see in a small animation. The particle properties are as follows. We use approximately 949 particles to reach an initial particle volume fraction of 0.5. The particles feature a size distribution which is realized by dividing them into 3 classes as shown here. The particle density is chosen as 1 kilogram per cubic meter. This makes our life easier when normalizing the results. The stiffness, i.e. the Young's modulus, is varied, as you will see later. The friction and coefficient of restitution have been chosen as typical values. Finally, I would like to note that the stress calculation is performed over the whole volume of the simulation. You see how this is done in the input files that are available on the iMooX platform. Before we start with the presentation of the results, let us look at the preparation procedure, which is quite important for this benchmark case. First, we deposit the particles in the simulation box. To achieve the relatively high particle volume fraction, we need to do this. We do this by injecting the particles into a somewhat larger box and then let them sediment under the action of gravity. Note that a direct insertion would not be possible simply because the algorithm for insertion is not smart enough to pack particles that dense. Of course, the top wall is deactivated during this first phase of the simulation. Second, the top wall is activated to ensure particles cannot exit at the top. And third, we remove gravity and let the particles relax under zero gravity conditions to reach a state with no significant overlaps between the particles. We also artificially slow down the particles such that they do not move at the time instant we initiate the compaction cycle. The compaction process itself is relatively simple. We just move the top wall downwards. Now we are ready to look at the results of the uniaxial compaction process. On the left we show a video of the preparation process and the compaction process. Here the particles are colored according to their velocity. On the top right panel we show the results using lights as the DEM simulator. The normal stresses as well as the pressure is plotted as a function of the particle volume fraction. This is how it is typically done. Similar as for the pressure in the regime map for shear flow, we have seen earlier, the stresses remain small up to a certain particle volume fraction, which is close to 0.58. Then the stresses grow several orders of magnitude. At high compaction states, this increase is less steep. This plateauing behavior is mainly influenced by the contact force model, which in our case was the classical Hertz model. The interesting question is now, what does the non-smooth DEM predict for this compaction process? And not surprisingly, we see that the LMGC90 code predicts strongly fluctuating stresses, reflecting the behavior of a system of infinitely stiff particles. Also, stresses beyond a particle volume fraction of 0.6 just skyrocket. Again, this is due to the extremely stiff particles that are simulating when using LMGC90. Clearly, for strain-controlled compaction processes, such as this uniaxial compaction, this non-smooth DEM code is not really useful. We close our discussion of the uniaxial test case by an investigation of the effect of stiffness when using classical soft sphere DEM, meaning we used lights to prepare the data shown here. On the left, there is again the data for the softest particles that we have already shown on the last slide. These particles have a Young's modulus of 10 to the power of 4 Pascal, so 10 kilopascal. If you look closely, there is an appreciable difference in the normal stresses. The ZZ stress, the one in red, is significantly larger, something that is also our intuition. In the center panel, there are results with a 100 times larger particle stiffness, i.e. the Young's modulus was chosen as 10 to the power of 6, so 1 megapascal. As can be seen, the stresses plateau at a stress that is approximately 100 times larger, but the shape of the curve is quite similar. The differences between the normal stresses at the highest stress levels appear to be smaller. In the right panel, we summarize results from our stiffest particles. Also here the behavior is qualitatively the same, but of course the stress level is again approximately 100 times larger or higher than in the center case. To summarize, the stresses for this extreme compaction process scale with the particle stiffness, thus normalizing the stresses with the Young's modulus Y is suggested, and this is also what is observed in the scientific literature and in real-world applications. Scaling stresses in compaction applications with the Young's modulus of the particles yields a master curve for the compaction behavior that is almost independent of the particle stiffness. This is exactly what we want when performing soft sphere DEM simulations, which are the only choice for these processes.